Hello. So let us wait for a few more people to join and then we can start.
Hello.
Yeah, hi. Hello.
Yeah, hi. So you are doing your PhD from IIT Gandhinagar?
Yes, right.
Okay. I am also in Gandhinagar. Like I am doing from DAIICT.
What's up from DICT? So I taught at DICT last semester. You must know Professor Rachid, right?
Pardon?
Professor Rachid. You know Professor Rachid Saya?
Yeah, yeah. He
Yeah,
he did his MTech from here and then he had done his PhD from IIT Gandhinagar.
yeah. So I was a TA. I worked as a TA with him last semester, I guess.
Okay.
So he was taking this machine learning course, I guess, advanced machine learning course. So what is your topic?
Pardon?
What topic are you working on?
Yeah, it's again the same deep learning and like data analysis, those
I see.
things. The topic exactly is not defined. Like it's I've taken admission like last year only.
Okay, that's fine. So who is your guide?
It's Dr. Bakul Goyal.
Acha.
Who's your guide there?
My guide is Professor Anirban Rajgopal.
Okay. And
So he was
your
also,
area, your
hmm.
topic must be defined by now, na?
Yeah. So right now I'm looking into privacy preserving machine learning, and also I've looked at numerical linear algebra type of problems.
Okay. Yeah, it has so many applications. It's difficult to choose actually.
Yeah. It requires some time. So yeah, but
Yeah.
with time you can narrow down to a specific topic if you,
Yeah.
but it takes time. Yeah.
So you are staying in the campus itself?
Yes, I am staying in the campus.
Okay. So I'm not sure if there's anything happening there or some conference here, like uh,
Oh. So I think there will be a winter school in the city from the
um,
mid of December, I guess. AC
in the
winter school.
starting of December there is something.
There is a
Um,
fire conference, I think.
okay, in DAICT itself.
Yeah.
Okay,
And there is also some winter school for women, especially. I think winter school for data science.
okay,
So we got that mail a few days back, so you can check that out.
okay. Yeah, if you come here, then you contact me. Like I'll
Yeah,
try
yeah.
to meet you.
So I think you will have my email ID. So yeah. Okay.
Yeah, I'll email on your ID.
Mhm. Sure. So your exams are on 29th, right?
Exam of deep learning.
Yeah.
It's on 2nd November,
Oh, it's a second. So you have
and
to.
I have two exams on the same day. One is deep learning and another is Python.
Oh, acha, you also taking the Python course.
Yeah,
Okay, so I think no people, others will want to be joining. So yeah, you can start. So I think the questions will mostly be the, because I've never given an NPTEL exam, so I can't say for sure what the type of questions will be. But it should be of the same level as you have seen for the assignments. So yeah, if you have any doubts, can, yeah, we can discuss those doubts, or if you have any problems in the assignments, we can also discuss that.
So this course, it hasn't covered like dense net or transfer learning, all those things.
Yeah,
So
those things have not been covered. But I guess if you go on YouTube, there is a, sorry, let me share the link. So that has a part two of this course as well. There you will find these advanced topics like transfer learning and so on.
okay, so this is just the basic.
This is just you can say an introduction type of thing.
Okay.
Introduction for various, let's say various algorithms. Some basic algorithms are different.
One thing which I am facing difficulty is like when the questions are like numerical type, uh,
Acha.
calculating the parameters,
Hmm.
all those things that I am not sure. I mostly get the answers wrong. Sometimes I'm not sure. Like if we have to, like suppose for CNN, if they have given certain thing, then do we always take a bias for the filter, or
So
like
actually that will be mentioned in the question. So you have to do it in two setting. If there is a bias, so you will have an extra dimension to add. Or if that is not mentioned, you do not have to take a bias. So it will be explicitly mentioned. It should be explicitly mentioned in the question
so if
because
it's not mentioned, what should we assume?
so you assume that there is no bias. So you just have some weight matrix W, and so if there is a bias, you have Wx plus P, right? And so your weight is your learnable weight, learnable dimension is for the weights as well as the bias. But if it is not mentioned, just don't consider the bias. Just say that okay, I just had this data matrix. Because if you are given some architecture, you just have to consider the sizes of the networks given in that, sizes of the neurons given in that architecture. If there is a bias, I think it will be explicitly mentioned that there is also bias. So if it is not given, you don't have to include that in the computation.
So I was thinking if you could like show us some questions like just
Yeah,
for our practice.
yeah, yeah. Yeah. Give me a few minutes. Uh, I am. I have some questions, but before that, yeah, if you have, can just ask now. Let me. I'm trying to find the link actually.
Hello.
Yeah, hello.
Yeah,
Uh,
so one query I had was in one of the lectures, there's a topic like relationship between PCA and SVD.
yeah, right.
So, like, what are they trying to say basically? Like conceptually, just the concept.
Okay. So, let's continue this. So you're able to see my screen, I guess. So the question is relationship between PCA and SVT. So for PCA, so what are the steps for PCA basically? So you are given some matrix X, and suppose it is a n cross D matrix, right? And now you want to project this X to some lower dimension, some low rank approximation. Say you have X hat, and instead of D dimensions, you want to say that no, I just want the K most important directions. So what is the process for that? First, you separate the feature-wise mean from this X. So suppose X has D features, right? So you subtract the means of each of these D features from each of the columns of X. So that is X minus mu. Then the second step is you construct. So this is the PCA algorithm actually. You construct the covariance matrix. The covariance matrix is basically 1 by n x minus mu transpose x minus mu. So for convenience, let us say that this is some x hat. So this is basically 1 minus n x hat transpose x hat, right? And now if you want to find the principal components, your principal components are the eigenvalues of this eigenvalues and for
Mu
eigenvectors.
mu mu is the
mu
mean.
mu is the mean for this. So mean is so suppose mu. So mu we have mu1 up to mu d. So your d is the number of features, right? So mu1 is the mean for first feature, and similarly mu d is the mean for the dth feature.
Okay.
Uh, this is clear, right? So because this is an n cross d matrix, so each of these feature will have a mean, and now for each of these feature you subtract the mean from that.
Yeah.
And
Okay.
then suppose after you subtract that you get some matrix, say x hat, and so you construct the covariance matrix, which is basically 1 by n of x hat transpose x hat. And now the principal components are the eigenvalues of this matrix, x hat transpose x hat. So the largest the largest eigenvalue eigenvalue slash vector is the first principal component, and second one is the second principal component, and so on. So if you select, say, if you compute the k largest eigenvectors, you have the k principal components of x. So what we say is eigenvalues of x hat transpose x hat are the principal components of X. This much is clear, right?
Yes.
Right. So now coming to SVT. So SVT is basically a factorization of matrices. So you are given some matrix X, and you can write it as a product of three different matrices. So you have P, you have sigma, and you have V transpose. So here U, so the columns of U, so you will have these columns. So U1, suppose X is here again, N cross D, and this U is your N cross, this is an N cross N matrix. So it will have N columns, right? You have N such columns. Now each of these UIs is N or is a eigenvector of X transpose. So sigma is a diagonal matrix. So we'll come to that what these are. Sigma is a diagonal matrix, sigma 2 up to say sigma t. So sigma is at the eigenvalues or singular values, let's say singular values of x, and v is v1. So yeah, so because you see x is n cross d, right? And now this is n cross n. Let us say this is n cross d. So what should be the size of v now? Because multiplying this we need an n cross d here. So what should be the size of v?
D cross N.
No, it should be d cross d, right? So you have n cross n here, n cross d. So multiplying these two, we get n cross d. And now again, if you multiply a d cross d, you get n cross d matrix, right? So let's look at it like this. So use your n cross n, sigma is your n cross d. So multiplying this, you get a something some n cross d matrix. And now again you have some phi, right? And phi is again your d cross d matrix. So multiplying this, you get the n cross d matrix. So phi is a d cross d matrix. That's clear, right?
Yeah. Yes.
So now phi will have this d columns, right? So each of these vi's, or let us say vj's, these are eigenvectors of xx transpose.
So this like
Sorry, so this is
how
x transpose x.
yeah,
Uh-huh.
how do we know this that they are eigenvectors of X transpose?
Oh, so they are calculated in this. So SVT computation is done this way. So how to compute SVT? So this is not required, but just for clarity, I'm saying this.
So what is the significance of this relation?
So okay.
I think it
Uh,
was mentioned with the autoencoders. So like in autoencoders, it this relation has some application.
it does not have some application. So one thing you should notice is this. So before that, so how to compute x SVT given a matrix X. So suppose you want to calculate the right, this V is called a right singular matrix. So what you do, first you compute x transpose x, and then you compute the eigenvalues of x transpose x. So if you see carefully, this is exactly the algorithm that was used for principal components, right? Just you have this extra step of x minus mu and this division by n. But other than that, this step is exactly same, right? You compute this x transpose x, and then you compute the eigenvalues of x transpose x to get the principal components of x. So what this means is that if you, instead of doing this principal components analysis in this way, if you just compute the SVD of x, then this right singular vectors, so these are also called right singular vectors. These right singular vectors themselves are the principal components of the matrix X. So that is exactly the relation
Okay.
between PC and SVD.
Okay.
So it is an alternate of PCA, right, sir?
Uh, it, it is not alternate, but it is, you can say that it is almost the same thing. Just for PCA, you have to do this, you have to subtract this mean, and you have to divide by n. But other than that, if you just compute, do this and compute the SVT of x, you can get back the principal components instead of doing the principal component analysis, or vice versa. It is not the alternate, just that the right singular vectors, these right singular vectors are the principal components of the matrix X.
So is there any policy or any technique that for which we have to go with a PCA and for which algorithm we have to go with SVD?
No, no, there is nothing like that. So because both of these are related, you can just do any one. And so if you want to compute your PCA, you can compute your PCA using this technique, or you can just do, if you have done an SVD of your X, you can just use the right singular vectors as the PCA. There is no policy. I think computing the SVD, sometimes, because practically it is that if you compute the SVT and use the right singular vectors as PCA, sometimes it may be computationally faster, but there is no such thing, no difference between these. So you can just do one of these and get back the principal components. So the thing is, because if you are doing this, right, you have to solve this eigenvalue problem every time. So here, if you do SVT, you get the V at once, and these are ordered. So this is the largest singular value, this is the second largest, and so on. So if you want to say take the top k principal components, you just take the first k columns of this v that you have right here, and then those are the k principal components that you have.
So basically, these two methods are used for to get primary features we are which has a very large variance,
Right, right. So
right?
yeah,
Okay.
right, right. So because if you have the number of features is very large, it is something that these features are not all important. You just want to keep the most important features. So these most important features are captured by the PCA.
Okay. And as you said, sir, in SVD that we can focus on limited columns also. So
Yes.
it is confirmed that means same is applicable for PCA also, and from left to right we have to go to focus the primary components or important features, or can we go from right to left also?
So right
Means
to left
me-
in this thing, in this direction, you mean?
Yes, 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 yes. So as
Yes.
you have mentioned that the vector
Uh,
V, which is a D of D, D cross D.
yes. Yes.
So suppose I need important features of this
Yes.
matrix, then I have to
Yes.
always go from right to left.
Left to right.
Yeah,
So left to
left to
right.
right.
Yes.
And
So
in case of PCA, sir,
so okay. So the way this because these Python libraries have already implemented this SVT type of algorithm, so they design it in such a way that these vectors are ordered in from the largest to the smallest. And for the PCA, so in PCA you have to compute the largest eigenvalues of this. So if you compute the largest eigenvalue, you get the first PCA. If you compute the second largest eigenvalue, you get the second PCA. Or if you just say that I am computing the, I am just compute the k largest eigenvalue. Let's say k largest eigenvalue.
So,
So that gives us the first k principal components.
okay. So correct me if I'm wrong. If for PCA we will get eigenvalues, and using those eigenvalues we will get automatically important features.
Yes. So important feature in the sense, uh, not the features exactly. So here you have some D features, right? But this will give us k important directions actually. So let us say, let us take a 2D example. Suppose this is my feature x1 and this is my feature x2. Some feature. I mean, suppose, so this is a famous example. My data is like this. So now I say that there is some, this is an important direction for the data, and the second important direction is this one. And now if I want to say, preserve the most important direction of the data, I'll just use this, right? So this is my first principal component. So because variance along this direction is the largest, right? So this becomes my first principal component. So that is what the principal component analysis preserves, the most important directions of your data. In a high dimensional space, this is just a two-dimensional space. So that is what the PCA really does.
Yeah, so while explaining the videos of this course, when they were explaining this relation between SVD and PCA, they have mentioned that the encoder part of the linear autoencoder is equivalent to PCA.
Yes.
How is that?
Okay. So okay. So now coming back to autoencoders. So how are autoencoders created? You have some uh, data here X, let us say, and now you pass it through this autoencoder block. Oh, sorry, this encoder block. You get some representation here, and then you pass it through a decoder block, and then you want to reconstruct X again. Then you want to reconstruct X. Okay. So forget about this part. Let us consider this part itself. So here your X is, say, for example, your X is 100 dimensional. Let us say your X is 100 dimensional. You have some vector of length 100, and this autoencoder, let us say the latent representation, let us say it is 32 dimensional. So you have a 100 dimensional data and you want to reduce it to a 32 dimensional data. So what are we doing? When I say that X is 100 dimension, it means that X has 100 features. And in the notation that you are using, so these 100 features is exactly D. And now when I'm saying that my latent representation, so this is my latent vector size, let's say. Latent representation is 32 dimensional. So this 32 is actually K, which is, that is we have 32 features. So what are we doing now? We are reducing our dimensions from 100 features to 32 features, right? So now suppose our encoder block looks like this. So we have an encoder block. Suppose I have my X here, which is 100, and now let us say that I use some 256 dimensional. Let us say this is a 250. There are 256 neuron here. Neurons here. There are 256 neurons here, and then this go to say your 32 dimensions. So
This what you are showing. This is for like uh, this is a under complete auto encoder.
I'm only showing the encoder part. So autoencoder has two parts, right? There is an auto encoder, there is a decoder. I'm just showing the
Yeah,
encoder part.
yeah, but this dimensionality reduction will be there only in the under complete auto encoder, na?
Yeah, under complete. Yeah, I want to go to a lower dimension.
Okay.
So now my neural network actually looks like this. If you are not using any convolutions or anything, just simple neural network. So it will be connected to everything. So this will be connected to everything and so on. This one. So just a simple neural network. So now let us say there is a weight matrix here. So now we are going from 100 dimensional, so quick exercise. We are going from 100 dimension to 256 dimension. So what is the size of this weight matrix? Suppose I want to do Wx, x is 100, and now I am going to 256 dimension. What is the size of this weight matrix? So my x is 100. So because x is 100, your last dimension should be 100, right? And now I want to go to 256 dimensions. So I'll just say that my this is a 256 cross 100 matrix. That is how we compute the dimensions of the weights. So this is a 100 dimension vector, and if I'm so because this is a 100 dimension vector, this number of columns in W should be 100 because it will multiply with each component of X. And now we want to go to a 256 dimensional space, so my number of rows will be 256. That is clear, right?
Yes.
Okay. So now I have a 256 dimensional or this much this size weight here. Now I have now here if you look at it, I'll have some pre-activations. Let us say A1. So this A1 is of size 256, and now from this I want to go. Oh, sorry. There are no pre-activations because we are talking about only linear encoders, right? So let us say we have H, which is of size 256, and now I will have a weight W2. So I will compute W2H, and its output should be in R32. So what should be the size of W2?
256 cross 30.
So because H is 256, so 256 will be there in the number of columns. 256 and 256 and 32 will come number of rows.
Okay.
Okay. So what is the operation happening here? So we have X here, and 2x we multiply W1. Now we get a 256 dimensional vector, and 2W1x we multiply W2, right? So which is a 232 plus 256 vector, and this gives us some vector which is in 32 dimension. But now if you look here, so you are basically multiplying two matrices with x. So let us say that your W2, W1 is some W. So you are just doing Wx. So you had x to be a 100 dimensional vector. Now you want x to be or not x. Now you want say h2, which is the latent representation, to be a 32 dimensional vector. So if I say that my weight is a 32 cross 100 matrix. So we can just have Wx, which is in 32 dimensions, right? So this W is actually what this is doing. This is reducing your dimensions from 100 to 32. So that is actually what PCA does, right? So in PCA also had a n cross D matrix where there D is a feature. So for our case D is 100. Now for each 100 we want k equal to 32. We have to do some dimensional reduction to go from 100 dimensional features to 32 dimensional features. So that means if your autoencoder is linear, and linear in the sense that you are not using any activation function, no ReLU, sigmoid, nothing. So then that means you are just doing a PC, principal component analysis of your data. You're just computing the 32 important directions out of 100, and you are computing a low rank approximation of the matrix X. So that is the relation between linear autoencoder and PCA. Is
Okay,
that
and when they are then so they are saying a linear encoder and PCA are related in this way, and
hmm,
then they are connecting it to SVD also.
hmm.
So like they want to say that linear encoder is also indirectly related to SVD.
Yeah, so linear encoder is same as PCA, and we saw before that PCA is actually SVD on the data matrix X. So that means if you are doing or not SVD actually, PCA is actually the right singular vectors that we get after doing an SVD of X. So linear encoder implies that we are doing our SVD of X and using only the right singular vectors for projecting to the lower dimension. So that is the connection between these two.
Okay, thank you. Another thing was unsupervised pre-training in DNNs. Like
Unsupervised.
pre-training. I don't think it's relevant now, but they have explained. They have one video for lecture for this only. So I don't know its application wise. Many things I don't get.
Okay, okay. So I think that is an important paper that came out in 2006, I think. Okay, and I think that was one of the papers that caused the author to win the Nobel Prize this time. So that whole thing is actually interesting. So before going into that, let us. I hope you remember what happens in autoencoders when we are doing talking about autoencoders. What actually are we trying to do? So, for example, here we have this 100 dimensional vector, and we want to learn a 32 dimensional representation of the image. So, not the image of the vector X. So, we want to learn a 32 dimensional representation of the input X. So that means uh, because we are learning, right? Because we are learning so what do we mean by learning? By learning, we mean that uh, we are back propagating some losses, and we're updating the weights so that this encoder learns a good set of W's such that this edge that you get here, this latent representation that you get here, this is a very good representation of X. So in 100 dimension, you have some, say, a photo of image of a cat. So that image of a cat is also captured in this lower dimensional space. So that is what we mean by learning. So in unsupervised pre-training, so again before going to unsupervised pre-training, how actually do you know that your model is learning? So before going to all that, I hope you remember what is the reconstruction loss that you talked about in PCA. So I showed you I showed you a demo, right, where there was an image of a cat, a colorful image of a cat, and then we took only the first 10 principal components and showed that using just 10 principal components we will be able to were able to reconstruct the image of the cat. And because we are not using all of the principal components, we are only using the top 10 principal components, we are not getting like the actual image of a cat, we're just getting a good looking image of a cat. By good looking I mean to say that there will be some pixels which are not correctly of the same color as the original image, but overall you get an image and then you know that this two belongs to the same image. So how do you describe the quality of these two things? So if I have uh, an image of a cat here, say A, and I do a PCA and reconstruct only some principal components, I get some image A prime. So I want that A should be equal to A prime in the best case, right? That if I have an image A and using some principal components, I should be able to get back the same image. But that does not happen because you are only using small number of principal components. So we define something as the reconstruction. So reconstruction loss means how much information are you losing because of using just a few principal components instead of all of the principal components. So reconstruction loss is basically the loss between A and A prime, right? So now coming to autoencoders, what is the thing there? So you have X, you have some encoder, you learn some data representation, you have some decoder, and then you try to reconstruct X. So which is the same thing that we're trying to do here. So because if, you must have realized by now, whenever you're talking about training neural networks, you how do you train? You get some output, you compare that output with some ground truth, then once you compare you get some loss, and based on that loss you update the weights during back propagation, right? So now we are trying to reconstruct that X here. So I will just pass X, it will learn some representation H, and using this H it will try to reconstruct X. Suppose I get some loss here, suppose it reconstructs X and I get some loss, it will back propagate again and it will update the weights. Over time this H, it will learn some H which which is able to reconstruct X satisfactorily. By satisfactorily, I mean the loss is small. The best case, the loss becomes zero, but ideally, that is an ideal case, but we want that the loss is small. Construct X satisfactory. So because so whenever we're talking about supervised and unsupervised, by supervised we mean that given a data set, we have some labels for it, and using the labels we try to reconstruct the image or the data set. Sorry, we try to update the weight so that we learn a good function which maps the input and the output. But here you see you are not using any labels here, you are using the input itself. So your input is X and you want to try to reconstruct X. So you're not using any labels on the input. So this is actually a unsupervised type of. This is actually unsupervised because you're not using any label information. You're just using the input to learn some representation of the input. So that is the unsupervised part of unsupervised pre-training. That is clear, right?
Yes.
Okay. So now coming to pre-training. So now for autoencoders, you see that once we have completed training this autoencoder, so this H learns a good representation of X. So now in that unsupervised pre-training work, what they did was, suppose I have some X and I have some, suppose it is a classification task. I have to classify into say monkey, cats or dogs, suppose some animals are there. So what we do is we pass X through a layer of neural net, some neurons, that is some layer of neurons, and now we try to reconstruct X again. So now doing this, we'll learn some good representation of X because that is what autoencoder does, right? So suppose we learn H here, or let us say H1. Now after H1, what we'll do is now we pass it to a second layer of neurons and we try to learn a good representation of H1. So we try to reconstruct H1. So now it will learn a good representation of H1. So let us say H2. H2 is a good representation of H1. And similarly, we can do a lot of this. So for H2, if we try to reconstruct H2, we'll learn some H3 and so on. So we train this thing first, then we train this thing, and then we train this thing. So now how does my network looks like? We have X, we learn some H1, which is a good representation of X. We learn some H2, which is a good representation of H1. Some H3, which is a good representation of H2, and so on. So now you have some very good set of features. So here you can say that H4 is a good representation of H3, H3 is a good representation of H1, this is a good representation of this. So finally, this is a good representation of X. And now using this, you can just use a classifier neural network, say some classifier here to say where what type of image that is. So what this is doing is that we are trying to learn the best representation in a few times so that by this time you have the most important information about your data. So this is pre-training, because the training real when you talk about training, we are talking about computing the output, comparing it with the labels, and then back propagating the weights according to the loss. So that is training, but you are doing this before training, so the training only happens at this point because you are computing the predictions here and then back propagating it here. So this is the training that is happening because with respect to labels. So because you're using labels here, this is a supervised learning. But here you are not using the labels and you are doing this before training. And you are just using the data set itself for reconstructing this. So now that becomes unsupervised pre-training. What is meant by unsupervised pre-training.
Okay, thank you.
So what type of questions do you want to see? So you have done your assignment questions. I have some variations of those type of questions. So which topic do you actually think you need to make something? Because there are a lot of questions.
Any like mainly which has numericals?
So okay, one thing is here is so we designed this neural network, right? So your X was a 100 dimensional vector. The W1 was 256 cross 100. W2 was 32 cross 256. So now if I say what is the number of parameters here, number of parameters in this network, so what will it be?
So it will be 256 cross 100 plus 32 cross 256.
Yeah, right. So you just have to, so parameters mean the learnable weights that are present in your network, and you just have to multiply this. So each of the entries of your weight is a parameter. So that is an easy one. So
So in this case, it's the weights, and in case of CNN, it will be the filters,
yeah,
like
there will be
filters.
weights as well as the filters. Yeah.
Okay.
So if you have k filters of size, so you have k filters, each is of size say 2 cross 2. So you will have 2 cross 2 cross, I mean 2 times k number of parameters there.
So it will be 100 plus 256 into 32 uh, plus 256 into 100, is it?
No, no, no. So this 100 is your input data. By parameters, what it means is what things will be learned. So this 100 is given as an input to the program. That is not a learnable thing. So that will not be counted. So the parameters that will be updated are each of the entry of this W1 matrix plus each of the entries of this W2 matrix for this example. So here you have 256 into 100 number of parameters plus 32 into 256. So these are the total number of parameters in this small network.
So only the learnable parameters are taken into account, and not the
Yes, yes.
hyperparameters or
No, no,
anything.
no. So when they talk about parameters, they mean what are the number of weights that will be updated.
Okay.
So you may get they will give you a small network and then they give you the weights and they may ask you to run back propagation say for one node. So suppose they give you some, so I'm not saying it will come. It's possible that I give you some networks say x1. So your first feature is say 0.5 and your second feature is say 20. So these are the two input neurons directly. So it is 0.5, this is 20, and now I pass it through a network. So suppose this has some weights say 0.05, 0.03, some random weights 0.01, 0.2, let us say, and then I'm doing let us say ReLU here. I have a ReLU here, and now suppose it goes to your output and you have some weight say 0.6 and 0.5 here, and let us say some of these are negative also. So one simple question is what is the output here? So that is simple, like you just multiply this and add this up. So when you apply ReLU, you make all of the negative terms to be zero and keep only the positive terms, and that is, and then once you get this output, suppose you get h1 here, h2 here, you just do 0.6 h1 plus 0.5 h2, and then you output it, whatever output you. So that can be a very simple form of example that, or numerical that you may get. I think you may have seen something like this in your exercises. So yeah, let you can get some question like if I ask you what is the advantage of using ReLU instead of sigmoid? Why do you, can anyone answer? Why do you use ReLU and not sigmoid? What advantage do is there?
Value has a flexibility for negative values also.
Yeah. So even for sigmoid you can have negative values. So the so would there
But
anyone else like
for
yeah
for higher higher values, a sigmoid become like stable, but the
yes
value is increasing.
yes yes yeah I think you're correct. So basically when we talk about sigmoid, so in these cases you need it will be good if you can remember how the graphs look like. So this is 0 and this is 1. So you see at higher values if sigma x becomes very large or it becomes very small, then your gradient almost vanishes. Your gradient almost becomes 0. So in that case, you don't need to, you won't update your weights that much because uh, your gradient is 0. So whenever you're doing gradient descent, your WT plus 1 equal to
So actually, ReLU the deals with the issue of vanishing gradients.
right. So if yeah right. So this is the gradient that we have, and if this is small, your weights will not be updated. So sigma is not helpful. But for ReLU, this problem doesn't occur, right? Because for negative ones it is 0 and positive ones slope is 1. And it's also very easy to calculate. So you may get something like this.
So
So there's a question.
there is one numerical in an assignment.
Ah,
I have posted it in chat. Maybe we
okay.
can discuss that.
So this is from assignment which we
Yeah, it is week 11 assignment of RNN. RNN.
propose that we need to develop
So here they have not given any choice like multiple choice. It's just give the answer.
okay. Okay. How many parameters are there in the network? So it is okay. So so we have 5 words, and each word is of is a 7. So each is embedded in the 70 cross is of embedding length 70, and your state vectors are of size 50 cross. Right. So let us draw the rail. So you have some axial You have some neuron here, and this output is also have to given out. Same given classification, okay, positive or negative. So yeah, so if it is one hot encoded, that means either your classes are either 0 1 or 1 0. Right. So now we want to and there is a state vector here which is given here, and this is of size st, which is of size 50 cross 1. So now what happens when you, so what happens to a state vector? You have some input x and you have some entry here. So what we do here is that because this state vector is added to wx, right? So let me open up the equation. One minute to open the equations. Or if you remember, you can just say what are the state equations that you have here. Hmm.
By state equation, you mean S,
Yeah. So what happens when x is given as an input? So if you remember,
SI is equal to sigma uh,
uh,
UXI plus WSI minus 1 plus B.
yeah. So you have some ux plus ws plus p, right? So these are your learnable weights.
Yeah.
So now your x is of size 70. So this is the input that we have. So this is of size 70. S is of size 50, right? So if this is 70 and you want to add these two things, so this ux should be a what's the bias, because it is one hot encoded. So your output has two layers. So your output will be a 0 or a 1 because it is one hot encoded, right? So because this is 70, you need some matrix which has 70 here, right? And now you, because see, you have x which is 70 dimensional, and now you want to uh, have it same as s which is 50 dimensional. So now you want a weight matrix which is 50 cross 70, right? If you multiply wx, or okay, like this is here actually. If you multiply ux, we get some vector which is uh, 50 cross 1 dimensional vector, right? So that is one part that you have. Now for the second part, you have So this second part, this is the W that you have here. So it transports from a state vector, it gives you a different state vector, right? So you get some, let us say, H here. So this is your H, and now you have, once you get this H, you get W times X, W times S. So your S was your 50. So you have S, and you want to construct at time I or time t, and you want to construct the S at time t plus 1. This is your 50 dimension vector. You need some W here, and this is also 50. So this is your 50 plus 50, right? So you have ux, you have wst. So wst gives you something, say, some 50 dimension vector, and it is, let us say it is some k, let us say some vector k, and finally you have this bias term, sigma of E. So this is ux plus ws plus p. So now you're, because this is one hot encoded, this, your number of output neurons is 2, right? So it has to be that this will be a 50 cross 2. So one bias for this one and one bias for this one. So we have 50 cross 2 here. So that means you have a 50 cross 2. So this is your P actually. There is a 50 here and there is a 50 here. So these things are learnable, these things are learnable, and these things are learnable. So what is the total number of this? This gives 35. This gives 2500, and this gives uh, plus some. Here they are showing 615. Why? Let me check.
Sorry, can you explain this again?
Okay. So this is your I mean to say the state equation, right? Whenever you are given an input x, this is how the forward propagation happens. You multiply x with some matrix u, you multiply your state from the previous time with some vector w or matrix w, and then you add some bias to that. So now see, because how do you compute this? You would have to take x to a 50 dimensional space, because your s is also 50 dimensional. So now what we do is, how do you take a 70 dimensional vector to a 50 dimensional vector? You have to multiply by some 50 cross 70 dimensional matrix, right? So this is your learnable matrix that you have. So this, you get this many number of parameters. For the second part, you have some state vector s, and now you also have to compute the state vector for the next time step. So now you have a state vector at whose size is 50. At the next time step also the state vector should be of time size 50. So how do you do that? You just multiply a 50 cross 50 matrix with it. So you get 2500 number of parameters there. And now they are saying that the outputs are one hot encoded. So by one hot encoding, they mean that we have two things here, and you have something here, some let us say just 50, 80, yeah, some 50 neurons at this place, and then you have some bias for this. So this is your say class positive, this is your class negative, and there are some bias terms which have been added here, right? So because each of these terms will have some bias, so then we get a 50 cross 2 matrix here. So this bias is actually 50 cross 2. So now if we add this all up, you get 6100 here. And
Oh, they gave the answer 6152. So
yeah, I think I'm missing some biases.
five. So where are these 52
Oh,
biases?
okay. Uh, so where are the biases? So if any one of you have computed it correctly, yeah, you can correct me if I'm wrong.
My answer was wrong. I wrote 6100.
Yeah, there are some extra 52 biases here. So where did they come from? Yeah, actually, I'm not sure about that. Uh, so any one of you got it correct? Uh,
So do the hidden layers these hidden layers they also have their bias.
you mean okay? Inside,
Like this 50
I
cross 1,
think
so
they
there
are.
will be 50
Yeah,
biases.
that is actually what I'm thinking. I think the hidden layers will also have some bias, but then mm, Okay, I think yeah, I made a mistake. So this is what is happening. This comes. So when we're talking about this these things here, we have x here, and now you have some 50 weights here, right? So this matrix is your U 50 cross 70, right? So now you will have a bias to each of these neurons. So that means you will have 50 biases here, right? Now coming back to this neural network, you have ST here, and now you are again taking it to 50 dimensions. So this is your weight matrix W 50 cross 50, and again you will have 50 biases here, right? And then in the last, then again in the last layer, because there are two neurons, so this is positive, this is negative. You will have a bias here, and you will have a bias here. So there are two biases here. So in total number of biases is 102. Okay, okay, there are missing some 50 biases. So I'm missing something. So I think this bias is also added somewhere. This is again because these are all 50 dimensional vectors. This is another 50 dimensional vector. So we have 50 plus 50 plus 50 plus 2 plus your 6000 parameters. So this gives us your 650 parameters. Is this clear? So this is, there is another bias vector that is added here. So that is another 50 parameters, because these are all your 50 dimensional vectors. And now adding this all up, we get 6152 number of parameters. Any doubts here?
So we have to add bias uh, for the hidden
Yes. So
layers.
in this question, they have mentioned that how many parameters are there including bias. Yeah. So
So
it's,
bias has to be considered for every hidden layer and for the output also.
yes, because for each neuron they are doing wx plus p for each neuron, so you have to add biases to each of the neurons as well. So any other question, any other concept? Okay, see that. Okay. 10. So we have input image of 100 plus 100 plus 1 with a kernel of size 3 plus 3 with 0 padding. Okay. And strike value of S. Okay. So we have, let us look at it like this. So we have a 100 cross 100 image. This is your 100 cross 100. And if you are using zero padding, so that means you have one more pixel here, one more pixel here, one more here. Right. So after padding, it becomes a 102 cross 102 image after padding. So now you do a, kernel is of size 3 cross 3 and stride is 3.
So can't we can directly apply the formula also here?
Yes, you can apply the formula because you know your padding size P. I don't remember from actually, but you have P, you have stride, and you have, uh, yeah, you know these two things. You know the size of the kernel, uh, so you can apply the formula here. I don't remember the formula, so
W minus F into 2P plus 2P
W
over S.
minus
F
F
uh, plus 2 plus 2P
2P
divided by S and plus 1.
plus 1. So it gives is 100 minus 3 plus 2 by 3 plus 1. This is 102 minus 399 by 3. This is 33 plus 1, which is 30. So this is the answer. I think this is the answer, right?
Uh, this one was with direct formula. Another question I have posted, it's again about parameters in CNN.
Okay.
The
Can you?
parameter questions are very confusing. I don't know.
Yeah.
Sometimes they write consider bias. Now in this question they are writing there are no bias terms.
Okay. So questions, week 7 question 2. Oh no. This. Okay. Before that, I'm going to this question. So now I will come back to this question. We have 100 cross 100 cross 3 image. Okay. Suppose it is 10 kernels, size 1 cross 1. Okay. Zip padding and stride of, value S. How many parameters are there? So what happens if,
Here when we talk of parameters, we have to consider the kernels, na, the filters only.
not the filters? Yeah, for this example, Yeah, for this example, only the filters. Yeah. So there are 10 filters. So that is 10. And now you are using kernels of size 1 cross 1. So that is, so you have 10 kernels of 1 cross 1. So these are now your this thing. And you are applying it for, so that your input image is 100 cross 3, right? So you will apply this kernel for each channel, for each channel, and each of them are separate. So you have 10 cross 1 cross 1 parameters applied 3 times. So you get 30 parameters.
Okay.
You are applying
Okay.
each
So
this kernel for each thing separately, each channel separately.
okay. So we have to multiply with the number of channels also.
Yes.
Okay.
Unless there's somewhere they mention that uh, you are using the same kernel, you have to multiply I mean the number of channels.
And if they had not mentioned assume no bias terms, and if we were supposed to assume bias here, then we
Mhm.
just have to plus one or plus how many?
So,
Like,
okay, so you can think of this when we say some filter is of size a cross k, it means that you have k neurons actually. You have k neurons. So that means you're adding a bias to each of these neurons. So you'll have k many biases. So in this case, you have just 1 cross 1. So in this case, there will be only one bias. If it is 3 cross 3, there will be 3 biases and so on.
okay, so one bias per neuron.
One bias per neuron, yes.
And for the number of channels, there won't be any bias.
No, channels is a part of your input. There won't be any bias there.
Okay.
So
It's
one
just telling
bias,
it's
yeah,
just telling the depth of the filter.
yes. So one bias per neuron, and there are 10 such curve filters. So that means there are 10 biases in this case for this example. So each of
Okay.
these filter is different.
Okay, so if we were considering the bias, then we had to do 30 plus 10.
Plus 10, yes. Right.
Okay.
So now I'm coming to week 7. That question. So what was the topic of bias? Okay, so the two models that have been given here are your F hat, the W naught plus W1 X. So this is basically you have some line, and the second model is W naught plus W1 X square plus some terms like this. So, okay, so this is some curve like this that you some curve like this. So now we want to know which of these, and our okay, our input is some cubic type of model. So this is something like this. Okay, see, so our input data looks something like this. And now let us look at the first model. If we feed only a line through this, so it will have a high training error, right? because it will not be able to learn these things properly. So it will have a high training error. And if I say that something has a high training error, that means it will have a high bias. So F1 hat will have high bias, right? And now let us take the second model, F, F, F2 hat. Yes. So F2 hat will be something like this. So basically, you don't have to draw this. You just see that this is a very high degree polynomial, right? This 3 here represents your function is something very curved like this. So for a curvy function, this thing does not have any curves. So if your function has a lot of curves and your candidate function is some straight line like this, so that means it will not be able to learn the function properly. You cannot learn some function like this using just a line. Any line will have only something like this. So that means you will have a lot of training error. That means you will have a lot of bias. But if you have a three-dimensional 3-degree polynomial here, and you are trying to fit a 5-degree polynomial to this, so that means it will try to learn almost everything. Even if your data is something like this, because it is high degree, it will learn something like this. That because this is higher, right? So that means it will overfit to almost all the points. So it will have zero training loss, but it will also overfit, and because of that, it will have a high variance. So F1 will have high bias because it is very simple, and F2 because it is very complicated, and by complicated I mean the polynomial degree is very large, so it will have a high variance in this case. So did you get that?
Yes, thank you.
So any more questions? Okay. You can just give me the question number. You can. Okay, the conflict.
Yeah, so in week 10, the first question.
Okay, so let me look at this contour curve first, and then we'll go ahead.
I think the questions are also different for different people. The
Oh,
questions,
is it?
yeah, yes, because I have seen solutions coming different for different people and queries also different by different people.
Oh, okay, so okay, I did not know that.
They have been shuffling the questions.
Uh,
Like randomly, they have been selecting from a set of questions and pushing different questions for different students.
okay, okay, so this loss function, they were given some function in W and B. Okay, so which question are you? Which part of the question do you have confusion about? Or which now? Okay, so the exam questions. So I've never given an NPTEL exam, so I cannot say. But I think it will not be tougher than this, the ones you have seen in the assignments. So the question you are interested in is the Hessian question, right? What is the determinant of HLB where H is the Hessian? Okay, so let us look at the function first. Well, now I want to do derivative with respect to W. So I get W here. Derivative with respect to P, because these are the parameters. You get 10 P. And now if I do double derivative here, I get 1. If I do double derivative 1 here, I get 10. And if I do derivative, I get 0, and here also I'll get 0. So my Hessian will look something like this: 1 0 0 10. This is my Hessian that I have. So determinant is basically product of, so determinant of HL is product of the uh, diagonal. If it is a diagonal matrix, Hessian is basically product of the diagonal matrix. Okay, so product of diagonals. Is this clear?
Yes.
Okay. Okay, so what was the next question? I don't know. Week 10, 12,
Yes, it was week 10.
week 10.
The question is basically there's a CNN given and then they are giving kernels of different sizes. Uh, and then they are asking for the same input image. Suppose we apply kernels of different sizes
Hmm.
and the stride is one with zero padding.
Ah,
Which kernel will shrink the output the most?
okay, so oh, these like there is 41 cross 41, 17 cross 17.
Yeah, yeah.
Those things. Okay, so the larger the kernel is, no, one second. So larger the kernel is,
Okay,
more
more
the
will be
string.
the
Yeah,
shrinkage.
yeah.
Okay.
So because if you are using a 41 cross 41 kernel, you are summing together this 41 cross 41
So,
size
so
image.
my query was
Hmm.
like a shrinkage in terms of length and breadth will be there, but
Yes.
the depth would be increased now. So, are we talking of shrinkage only in terms of like length and breadth?
Yeah, yeah. Only the length and breadth. So because even if we are given only one kernel, but it will be applied across all of the depth. So this is 10 depth 10. So it will be applied across depth 1, across depth 2, across depth 3. So all of these length and breadth will anyway be reduced or shrunk or shrink. So yeah, so the larger the kernel, the more shrinkage that you will get because it will combine more number of pixels together.
Okay. And also, like every time the first part of this question, like every time the depth of the kernel will be same as the number of channels.
So the kernel does not have depth. So kernel is a 2 by 2 type
So
of.
in the first part of this question, they have asked what would be the depth
Oh,
D of the kernel. So
okay, okay. So okay. So by depth D it means that. So that is what I'm saying. You will apply one kernel for each channel. There will be a different kernel. Now, if you all place all of these together, it means you have a one cross D. So D is your 10 dimensional. I mean 10. Yeah, 10.
yeah, so
Because
even if the kernel size was 3 cross 3, even
uh,
then the depth of the kernel would be 10 only.
because you will have 10 3 cross 3 different kernels. So if you place all of these together in a tensor, so that becomes a 10 cross 10, 10 cross 3 cross 3, or 3 cross 3 cross 10 type of tensor. So that
So the
depth is
depth of
different.
the kernel is same as the number of channels in the input image.
Yeah, yeah. For the first layer, for the later layers, it will be different. So the first layer
Okay.
is like that. So say suppose I am using 100 10 cross 100 3 cross 3 cross 10 images, right? So now we have 100 kernels, and these kernels are of size 3 cross 3 cross 10. So now the output will be uh, 10 cross some, I think 100, some 100 will come up there in the output. So the next layer of kernels will have 100 as the depth, because it will have to look at all of these different depths. So it will depend on what type of calculation, of what type of layer you're applying.
Okay. Then in assignment 9, question number 8, it's about the glove representations.
Okay. So question now, I think for me it is question number 9. So there are some parameters 0, 0.02, 0.0, all this, right?
Yes, yes.
Okay. So suppose given the learning representation of what's link of. So what are these types? Okay. So I don't. Uh, so if we go back to glove. Uh, so what lecture was on glove? 9.
It was after skip gram.
Uh-huh. Right. So for this you will have to look at the equations in glove exactly. You have to. Okay. Okay, so for this question, so the optimization problem for clock was this minimize for two words VI, PJ, VI, summation over IJ, VI transpose PJ plus J is log of Xij square. So you have to minimize this thing, right? So this was the optimization problem of log plus given. So these things we know log of this log of say 0.03 or something. We know these two things. Vi is say 0.02 and this is 0.05 that we have here. Okay, so so now we know that the words are similar. No? So here we have been given that the words are similar. So if words are similar, that means your phi transpose pj is high, right? This should be large. Now in this thing, so suppose we have that because we have to minimize this and we have learned the perfect pi and pj's. So that means we have pi transpose pj plus pi plus pj minus log of xij equal to 0. We have the minimum for this. So that means if I say that pi transpose pj is equal to log of xij minus pi minus bj. Now this is high, right? And these two things are small, like 0.02 and 0.05. These two things are small. So this is high and this is small. So these things should be high, right? So for the given options that we have, the highest is 0.8. So that is how you get it. I hope that is clear.
Okay, but the answer is like it's xij is equal to 0.8. It's given like that. Okay, so just
So
the highest value.
highest, yeah. So log is like this. If xij is high, log of xij is also high.
Okay, thank you.
So yeah, if there are no more questions, I guess so you can leave. So all the best
Yeah,
for your
question.
exams. Yeah.
questions are ready, but
Yeah.
time is over. So
Time is almost over right now. So all the
thank you.
best for the exams, and yeah, it was nice interacting with you about this last 12 weeks. So all the best.
Thank you.
Thank you. So I'll upload these lecture to YouTube, and I'll upload these notes also if you want to go through.
Thank you.
Thank you.